Hey everyone, welcome back. So today I'd like to start off. I mentioned in a couple, two streams, I believe, what I was making the other day. So the suggestion was to bring it to the next now. So this is what I made. It's Lego. It's pretty cool. This is not the one that when you move the wheels, you can see the pistons and stuff. We do have one of those, but it's really big. It's really big, and it's upstairs. It's probably like most of the size of my desk. Yes, but I made a Red Bull because that's my team. I like both Max and Yuki. I mean, Max is my number one. Yuki's awesome. It's really sad to see him going. He really got a raw deal there, but I've got another, where is it? I've got another Red Bull right up there that has Max on one side and Checo on the other side. So that was from last year or the year before. Can't remember, but yeah, that's what I was doing. So there, you got to see my little Lego build. I really do like Legos. I actually have a picture of the other ones that I built. Those are 3 plants and 2 plants, a bonsai tree, and 2 little mini, like this big, shops, Japanese shops. So yeah, that's my little secret interest, and now you guys know about it. But today we're going to be going back about 1.38 times 10 to the 10th power years to the Big Bang. So this is a topic that, even though it was the first thing, it's not the first thing you talk about, because there's other things you need to understand before you can really get into the details. And part of that, which I haven't gone over in this stream, but there are plenty of other streams or videos that talk about math and even just explaining what certain numbers mean. So I know most of you here already know it, so I'm not gonna go into that because I don't think there's a need to. I think I'm pretty confident that you all know what powers are, what exponents are. And that's really all you need to know here when talking about this. So we're going to talk about the Big Bang, and that was, to our knowledge, 1.38 times 10 to the 10th years, and so that would be 13.8 billion years ago. The first seconds are really the most important ones to understand, because, or not even the first seconds, like the first second, everything that happened within the first second. And the reason why is because the first second, everything that exists now came to be then, within the first second. And I know that on several other occasions, like during the remake of Cosmos, they talked about if you were to put the entire life of the universe in one calendar, that we would have happened in just the last, like, not even second of the last day of that month. So everything that happened between then and now, this past second has been pretty important for humanity, but the first second is the most important for the entire universe. It started as an incredibly small, like so small, um, the 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 study of quantum mechanics has to come into play when you talk about how small. So this is called a singularity. It was incredibly dense and incredibly hot, and it just started to expand rapidly. This expansion is faster than light, and I know that from that a lot of people will wind up asking, but nothing's faster than the speed of light. Well, that is true. That is the speed limit within our universe for anything that has mass, but space itself, the universe itself, doesn't need to abide by that. The universe is not in the universe. I guess that's kind of as I guess debatable is a good enough word, but that would probably spark some debate to say the universe is not in the universe. Just like water being wet or not wet is a debate. I understand both sides of that argument too, by the way. So we call this expansion not the expansion, we call it the inflation. This expansion, as I said, is the expansion of space itself, and that's a really important thing to remember. Not an expansion within space, like within the universe. So it's not the same as if you were to throw a bomb on the ground and watch it explode. Because that's already there. If you were to compare it to, there was nothing else outside of this bomb, and only the stuff inside the bomb existed, and then it exploded. That would be a better comparison. And then everything inside of that is what became of what we see now, and this vast amount of space we have here. So keep that in mind, especially when considering how fast it was actually going. So I like to start with the Planck era, which was 10 to the negative 43 seconds. So that would be 0.42 zeros and a 1. Very, very short amount of time. Great, I got a bug in my house. Okay. So this time, the temperatures were so hot that they ran what is predicted to be about 10 to the 32 Kelvin. That is the hottest thing that I can think of. I mean, that's a lot of zeros. That's a lot of zeros. The mass density was so packed in that it was approximately 10 to the 93rd grams per centimeter cubed. So if we compare that to the core of our sun, the core of our sun is only 160, well, only, that's still a lot to us, but it's only 160 grams per centimeter cubed compared to the approximate 10 to the 93rd. That's very dense. And a Planck length a Planck length is 10 to the negative 35 meters. So that's just a little that would be 34 zeros followed by a 1. Not the other way around. It's very small. Then we can move to a little bit after that. So between 10 to the negative 36 seconds to 10 to the negative 32, that is when the fundamental forces that we know now, so that's gravity, electromagnetism, the strong nuclear force and the weak nuclear force, that's when they separated. Because before then, they were thought to be in one singular, like one put together. So they were thought of as just one, like, I think it was referred to as the super force. I think that's what it was referred to as. And so in this time frame, which is again very short time frame, still a lot of zeros before the 1, that's when the fundamental forces split apart from each other and became the 4 separate forces that we know now. And the particles, such as quarks and leptons, that's when those were created. And quarks, so in order to have protons and neutrons, you need a tri-pair of quarks. So quarks started to, with these fundamental forces and this growing but still dense compared to now. So these quarks began to combine together and into their pairs of 3, and that created the protons and neutrons. So a little bit later we will talk about, or I will briefly go over anyway, how these particles started gaining their mass and how they have the mass that we know them to have now. Okay. So, another thing we can ask is, how did this matter that was just created? How did this become from just pure energy? So the expansion was thought to be just pure energy. How was matter formed from pure energy? Well, if you think of it in the reverse way of how... Zoe, hi. Hi. Let's take a little break for a second. Come here. And I'm gonna bring my dog. Oh, you just hit me in the nose. Oh, who's a good girl? She is very furry right now. She doesn't like the shaver, and she's very old. So, I like to respect her boundaries with loud noises and things by her ears, and her eyesight is getting worse. She is 14, and I've had her for that whole time. And she's a very good dog. She's probably down here because she needs to go potty and probably needs to eat. But you guys get a little doggy show for a minute, and I will take care of her after. Okay, go lay down. Good girl. Go lay down. Okay, now back to the program of the night. Okay, so if you think of it as a reverse scenario of how an atom bomb works, right? You have these particles and you force them to separate, and when that happens, it causes this chain reaction to occur. Well, it's not technical. I am not a bomb expert, but then the act of doing that creates this incredibly hot energy that is the bomb itself. It's so hot and so high energy that it can melt ships to the sea floor, as we saw. Or not we, but long time ago. So that also, we can look back at Einstein. I mean, E equals mc squared is, the act of, they're saying that energy and matter are essentially the same in different forms. Like water and ice are the same thing, but they're in different forms. So if you were to do some algebra on that, you would find out that mass is equal to energy divided by its speed. And so in this case, it would be m equals E over c squared. But you'd have to, in the reverse is how matter was created at the beginning. The hot state of this quark soup, and yes, it was very liquidy, but not like the water liquid we know here on Earth and what we experience every day. But it was more like a soup, not a gaseous as they thought originally. So this hot state of the quark soup then turned the energy into the particles. And that's where you have to keep in mind that the expansion was faster than light. So the equation of finding out what matter is a simple algebraic transfer of E equals mc squared to m equals E over c squared. This energy became matter, and in the creation of the matter came antimatter. And in this time, they were created the same. It's common understanding through the science community that there was the same amount of each on either side. And then the common question after that from everyone else in the world is, well, if there was the same amount, then how do we exist today? Because we exist from matter. We're not getting bombarded by antimatter every day, and that just wouldn't be a pretty sight, would it? So what did happen with that? There's a couple theories on that one. Antimatter has a shorter lifespan, so as it went on, as this fight between them went on and they were annihilating each other, it is thought that the short lifespan played into them dying off a little bit earlier than they could meet their counterpart, which is also backed by the fact that they were still in the expanding phase. We are all still in the expanding phase, but that would give some further distance between them, so they die faster. And after this fight ended, matter won, and that's good for us because we exist because of matter. Oh my gosh. I do love dogs. Well, mostly my dog. Don't really know about everyone else's. No, I'm kidding. I like dogs. I like cats. And I just really like animals. And no offense to all of you, but I probably like animals more than I like people. I'm sure that plenty of you agree with me. Anyway, so there was a phase where matter and antimatter were just annihilating each other, as I said. But we came out on top. Okay. Now that we've recovered that, one thing that is also important to know, well, I think it's important to know, is that matter obviously doesn't annihilate itself, or else we wouldn't be able to clap our hands or touch microphones or mice, whatever. And that's the same with antimatter. Antimatter doesn't annihilate itself. That wouldn't make any sense. So, I mean, there could be a world out there where antimatter was the one that came out on top, and there's an antimatter world. But luckily, we don't have parts of this world that are like that, or else we would have a lot more explosions around us. Just to put that into perspective, an apple-sized matter. So we'll take an apple and take an anti-apple and then throw them together. It would have the same effect as a 10 megaton bomb. That is, if I remember the numbers correctly, about half of the megatons that they used in Bikini Atoll. So, smaller than that, but that's still very large. So we are made from this matter, but all of the matter that exists now happened during that time, which is why I said this first second of the universe is the most important for us to really understand. And even though it started out very small and it grew very rapidly, and the numbers can kind of be a little bit overwhelming. The speed, for one, the amount of zeros before or after a 1 in everything I've mentioned so far, between the temperatures during the Planck era, the mass density, and just the fractions of a second that I've mentioned. These are numbers that are kind of hard for us to wrap our brains around, but the important part of the message is that these things happened, not really the time frame. So, as long as you take away the order that things happened, or even just what happened at all, that's a win for me. That is my goal, is that you take away at least one thing from any of my videos. When this matter and antimatter collided, it started to radiate, and it released a lot of energy and a lot of light. These are like the first light that ever existed. All of the energy and light that was emitted during this very short period of time still exists, but as we know from looking at distant stars and watching the spectrometer, wavelengths will stretch out. And when you see radio observers, they are measuring radio waves, and JWST measures infrared. Chandra is X-ray, and Hubble is both he the telescope has both visible and infrared. So these all capture different wavelengths, and so the energy in the light that was emitted during that time was in the very short form of gamma, which is what we see from our sun, but this stretched out over the time, over this billions and billions of years, into what we now call the cosmic microwave background. And so microwaves are the longest wavelength on the chart. So it has shifted so far to the red that it is now microwaves rather than gamma radiation. This is also often referred to as CMB, so if you ever hear anybody else talking about it, you know, oh, CMB, that means cosmic microwave background. Okay, this background radiation, it's all around us, and we actually can still see some of it. Yes, I know our eyes, when we look up at the stars, we can't see microwaves. You know, when we turn on our microwave, we can't see the actual waves coming out of it. But you can see the CMB. This is a very interesting fact that I learned quite a while ago, but then I just rewatched something from a while ago and I remembered, because we just don't have this anymore. So I know that most of you will know what I'm talking about. I don't think I have anybody following me that's younger than a millennial, I believe. Except for one. I know that there's one child that watches some of my content, and he is actually a child. He's my oldest son's friend. But for everyone else who is my age or older, which is most of you, I would assume, we can see it if you still have a TV that can actually click through channels. So I do not have this TV anymore. I used to, but I don't. I have a TV now that is an Amazon TV, and you know, we can stream. I have Sling as my cable instead of a local cable provider. So I don't believe that my TV, if I were to put it into the like antenna mode, I'm not sure if it would actually do this. But if you do have a TV like that, go try this right now. Or maybe after the video. Either way, if you turn on the TV and you go to a channel that doesn't work or you can't pick up the signal, some portion of that static is going to be from the CMB. Or if you're driving in your car and you have the radio on and you're scrolling through channels to try to find your favorite channels, those in-between staticky channels are picking up these microwaves. Now, I'm not saying all of the static on your TV is from the CMB. There's other factors that play into it, like interference from the signals trying to reach further places and just our atmosphere alone. But some portion of that is from the CMB, and that's a very cool fact, and you can try it if you want. So before I move on to talk about my favorite subject, which is CERN, I would like to, I feel like maybe some of what I said earlier wouldn't make that much sense because I didn't talk about the time after I talked about 10 to the negative 36 to 10 to the negative 32. Now, looking back at my notes that I took, I did not mention time at all in here, and so I just don't want anybody thinking that all of this stuff happened in that time. So let's just go over that. So without mentioning the time specifically, I'm just going to go in order. There was the Planck era, and that was the hot, very dense time just after inflation started. Then you have the fundamental forces separating, and then you have inflation, the inflationary period ending, but expansion still continuing, and that then sparked the reheating, which is what created this hot, dense, soupy substance. Soup is really the best word to think of because it wasn't fluid like water. It was more thick, and the universe was still incredibly hot and dense. Too hot for quarks to bind together to create protons and neutrons. So instead, it was what was referred to as a quark gluon plasma. So that's what the soupiness was. More like plasma. That I could have said that earlier. So then that's when the matter antimatter after that. That would be quark and antiquark, lepton, antilepton. That's when they started annihilating each other. And then that's when the matter came out on top. So this last little bit was the last second, no, the last of the second. After the universe cooled enough, that was when the quarks could combine into their threes and create the protons and neutrons that were needed to make the light and the energy and become the CMB that we see. So, and another little add-on would be that this last of the second, right around the 1 second mark, was when the universe had also cooled enough for neutrinos to take shape. And there's actually also a cosmic neutrino background, but that's a lot harder than the microwave background to detect. Neutrinos themselves are actually harder to detect because they're so small. So all of that first second was so violent and just very important to understand, because that was the most that had happened in one time during the Big Bang. So there is there's the little breakdown for you. So now we can move on to talk about how we got mass. How did these particles get their mass? That is where the brilliant physicist Peter Higgs came into play. In 1964, he came up with the theory that there was a field that the particles could move through, and as they moved through it, could gather just more and more onto themselves, which then would create their mass. And so in order to essentially confirm this field that permeated the whole of the universe, which is now referred to as the Higgs field, they had to they thought that there must be an accompanying particle to go along with this field. And so that was in 1964, but it still took over 50 years, I believe, long pause there, sorry, to actually find any confirmation of it. So this is for a few reasons. There was not a high energy program going at all. And as we found out with the colliders that we do have here, at least here in America, the one that's under me and the relativistic heavy ion collider in New York, they just were not big enough. And actually, I believe it was in New York where they found out that the inside of the protons were this plasma liquid, and that then confirmed the quark soup. But we did not have one big enough here to detect the Higgs boson. And that also could be because they have a very short lifespan. So their lifespan is about 10 to the negative 22 seconds. That is a very short lifespan, and it is hard to find a particle that dies that quickly and is also small. So they would have to wait a long time, and they did. So in 2010, the Large Hadron Collider, or LHC, finally began its high energy program, and then it took 2 years after that for them to confirm finding a Higgs boson. So on the screen I have the comparison with the quarks, the leptons, and then the Higgs boson. So this Higgs boson is the particle that then made up the Higgs field, and this is how the particles get their mass. So particles get their mass by interacting with this field. The same as if you were to take a ball, maybe just like one of those really light ball pit balls. If you take one of those balls, you can imagine that light ball is the original particle. And then if you were to take that ball and you were to roll it through some honey, and the more that this ball interacts with the honey, the more honey it gets on it, and then when you pick it up, it's heavier, and it's got different properties now. So that is the idea for the particles getting their mass through the interaction of the Higgs field, and therefore the Higgs boson. So as I can quote from CERN themselves, this mass-giving interaction with the Higgs field is known as the, I really hope I'm going to say this correctly, Brout-Englert-Higgs mechanism, proposed by theorist Robert Brout, Francois Englert, or I guess that would be Engler, and Peter Higgs. And as you can see here, this was when CERN published on their X account on July 4th of 2012 when they found the new boson. And so, as you see here, it says #CMS, and that's because it was CMS and Atlas that found this. So hashtag CMS. We have observed a new boson with a mass of 125.3 plus or minus 0.6. That would be giga electron volts at 4.9 sigma significance. So, of course, that was an amazing thing, and so says the thunderous applause. Of course, there was a thunderous applause whenever something happens in the scientific community. We all very much enjoy and are very happy. Unlike in other areas, like maybe sports, where when the other person wins, they're not so happy. But if one person in the science community wins, we all do. And that's a very important thing to take into life with you. So this mass is important to understand that this mass is actually 120 times the mass of a proton as a photon. That makes it the heaviest, not the heaviest, the second heaviest element. But because of its short lifespan, which I had mentioned was 10 to the negative 22 seconds, we could only rely on something as large as the Large Hadron Collider to find it. She's coughing. This old lady coughs over here. And this little graphic right here is actually showing, so this is showing the probability, the bottom graph is showing the probability, what happened when they actually did 300 dice rolls. And you see it favors the 3 more than predicted. But the top image is an animation of the reconstructed mass from Higgs candidate events in 2 photon decay. That bump in the graph actually corresponds with the mass of the Higgs boson. Okay, so I found this video. It's actually linked in CERN, and it's 3 episodes, but I'm just going to go through the first couple minutes or so of this, and I'm probably going to pause it too, so I can... But it starts out pretty cool. So there's a sound, and I'm assuming that sound is what they think it sounds like inside. I've never actually seen one, so they probably do know what it sounds like inside when they actually collide. So let's see if this actually works.
This is an animation of a particle collision in the Large Hadron Collider, as seen and reconstructed by our particle detectors. Now, what we usually say when showing these is something like, by carefully analyzing the particles that come out of the collision, scientists try to understand what happened there in the center. But how do we do that exactly? These are plots that were shown during the seminar at which...
Okay, so that first part, I believe they were trying to mimic the sound of them colliding. And so he's going to talk about the charts.
Which Atlas and CMS announced the discovery of a new particle in 2012. And we were saying something like, we have observed a new boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviation.
We observe an excess of 5.0 sigma in this region.
Everybody was...
So the standard deviation is very important when trying to confirm, well, really anything, but especially, something that small, and you're finding something that's totally new to us. I mean, that's amazing on them. With CMS and Atlas, that is really cool.
excited about the bump, the peak in the cloud, there was the sign of this new particle, the Higgs boson.
See, so he's referring to the peak that I showed in the animation. So I'm not sure if you can really tell, but this is just kind of like highlighting the peak. So it's pointing at it here, and then it just like blew it up a little bit so you can see it a little bit better. But this is the same as the one that I had on the screen. So this little peak right here, that is the detection of the mass of the Higgs boson.
But what are these plots really telling us? What's the link between such plots and the particle collisions? In this mini-series, I'll walk you through the Higgs boson discovery.
Okay, so actually, I'm just going to stop it there. 1 minute 10. He just kind of confirmed what I had said just now. And I can actually link these episodes in my community. Also, my community is open. You guys can all post on there too. So I figured out how to do that, and I did it. I opened it up for all of you. We can all interact on the community on YouTube. Or you can jump in my Discord. So here, let me come back here. So now that that's all finished, I got across all of the main points that I wanted to talk about. Of course, there's a much deeper understanding that can come of it, but that takes time. I don't expect everybody to just jump in head first knowing everything there is to know about how the universe started. We all learn at our own pace, and I'm here to just help guide people along. But as I said before, I hope there's just one thing that you can take from it. That means that I did my job successfully. And remember, just share videos on any social media network you have. I do not operate TikTok. Don't really care for TikTok. But you do have my permission to share some of my content on there. So remember to like the videos too. That's also very important. But sharing just helps get the word out there. And if you want to join the Discord, there's always a link somewhere. In the main description, there's a link, and I usually post in every video, but there might be some missing the link. But I know for a fact that there are links in multiple videos and in the main description. So I look forward to coming back with some more. Let's see. I think my next videos are gonna be about planets. So we might talk about planet properties, what makes a planet as well. Which, as you can assume, the debate on Pluto will probably come into there. But I am also doing a separate video on dwarf planets. Those are also intriguing, and I know my son loves those so much. He has a song that he sings that he can name all the dwarf planets. So I look forward to seeing that, and I will also be hosting a chat, just like the previous Discord chat. And this is open to anybody. You can jump in the Discord, you can chat along with us, you can even ask questions if you're not sure about something. But it will be on either just this video, just talking about the Big Bang, or if I decide to do it a little bit later, it's probably gonna encompass this episode as well as whatever comes in between now and the chat itself. So yeah, just if you want to be part of these chats, make sure you're in the Discord and look out for the events. Make sure that your notifications are set to ping whenever you are pinged, not just whenever somebody comments. I might have some other platforms opening up, like maybe Zoom chats and stuff like that, but for now we're just going to do Discord, and you can pass that on. Give the link to whoever you want. Share links to videos, share links to the channel itself. Your support really, really helps. Your support is what makes me want to keep making videos, because I really enjoy the feedback. So look out for my new videos. Look forward to seeing you soon. And remember to keep looking up.